The next speaker is Professor John van der Lindt. He is the Harold H. Short Endowed Chair Professor in the Department of Civil Environmental Engineering at Colorado State University. He has conducted nearly 50 research projects related to building and other systems related to earthquakes, hurricanes, tsunamis, tornadoes, and floods. He is the co-director of the NIST Institute of Standards and Technology funded Center of Excellence that Dr. McAllister talked about earlier today, and is headquartered at Colorado State University. The NIST Center of Excellence is a 14-university collaboration developing the computational resilience environment in core and engaging partner communities. So, Dr. van der Lindt, this is all yours.
Okay, thank you very much, Sherif. My pleasure to be here and to share some of the work. And I say some because the center is 14 universities with approximately 30 principal investigators, as well as collaboration with NIST researchers. So to give you just a quick overview, as Terry mentioned in her keynote this morning, we've been funded for about 5.5 years. The first 5 years was developing the open source computational environment in core, which I'll talk a little bit about today and then get into a detailed example, to standardize data ontologies and then develop a comprehensive set of test beds and hindcasts. And the hindcast will be the focus today. The second 5 years, which we're in the middle of the first year, is moving into measurement and decision science using in-core. So essentially applying in-core to these problems and to communities. And so that'll be our decision support and implementation, or essentially technology transfer. And then looking at, again, continuing to look at the data science and the validation of the whole architecture of the system. And so it's really moving from that knowledge creation, the science itself, into the knowledge implementation while still developing the supporting science. The National Academies, and many of you may have seen this, but the National Academies put a report, published a report several years ago, and they said a new kind of research is needed that can address the dynamic state of communities and their changes in risk and resilience over time, link information, data from disparate programs, and link research, data, and information with decision making. And so much of that aligns with what we're doing, as well as a lot of the presentations that I've seen so far today. In-core looks at the models the physical infrastructure itself, the economic health of a community, social services, or the availability of social services, all combined within information science. And I'll run through the platform, but there's some links on the bottom left there, and it's open source, available on GitHub, as well as a cloud computing platform, which I'll talk about. So essentially it takes the user from the initial damage and loss modeling, the impacts of that hazard, natural hazard on a community, and then into the interdisciplinary recovery, as well as then enables the user to look at alternative actions to enhance community resilience and to inform planners. Focusing on the right of the slide, you can see we have the ability to model individual hazards as well as multiple and competing hazards, physical infrastructure that you heard a lot about today. And then one of the key features of in-core is the robust social science and economic systems modeling capabilities. And so there's 5 test beds. There's actually 3 in-core right now, and the others are going in. The first was a virtual community called Centerville that we've talked about for a number of years. It's ironically the first, but not in-core. And it's perhaps the simplest, but it was a virtual test bed. Then there's Seaside, Oregon, the Memphis Metropolitan Statistical Area, which was part of the May Center originally, and you saw that highlighted in a few presentations already today. A new, in this most recent 5 years, the Mobile, Alabama test bed, which is just starting. Galveston, Texas, for hurricane modeling, and then Joplin, Missouri, which I'll talk about today for tornado, and then a field study in Lumberton, North Carolina. So there's two tiers within INCORE for hazard types. And the first is essentially completely contained within INCORE. And this is executed in INCORE, and it's essentially, for instance, a tornado, and it just brings in a raster file of an intensity over spatially. Tier 2 could be something like AdCirc or AdCirc-SWAN combination. These types of things. It could be for the earthquake engineers in the audience today, that could be a finite element model of a fault rupture, and then bringing in those intensities. And so it's brought in as a raster file. The economic modeling and analysis capabilities, INCORE uses what's called a spatial dynamic computable general equilibrium model. And these are state of the art. This was coded as an open source platform. I believe it's the only one in the world that's open source, because these are typically commercial, for-profit commercial packages. And so it took a team several years to do this here at CSU. It incorporates the infrastructure damage and population disruptions and dislocation, and then provides a range of economic and fiscal impacts, things like losses in production, wages, and jobs. The social science modeling and analysis, we look at things like population and employee dislocation, housing restoration and recovery, business interruption and recovery, these types of things. And it does this using a synthetic population allocation algorithm. And you heard, I think, a similar approach that Seth used that talked about a little bit earlier, keeping the sense. We can get down to the census block, but then we have to populate the individual households synthetically, because that information is not provided due to privacy laws. And then identify socio-demographic, socio-economic vulnerability characteristics, things like that, and then use those in these multivariate regression models. Complex system modeling and uncertainty propagation, things like we're looking to standardize, at least within INCORE, interdependency models, certainly dependency models. Interdependency, like many of the presenters alluded to earlier, is very complex, having that feedback. And so we model a lot of dependency and then some interdependency. Uncertainty propagation approaches, as well as what scalability and what resolution to operate the models at, so that you can inform a decision. So the architecture, hopefully this will play. So the architecture itself, it's a cloud computing system available to anybody. It's built with PyIncore itself, the INCORE web services, the web tools, and then the workspace, which is Jupyter Notebook. So here's a quick Joplin example I'll show. This is a building model. The graphics aren't great here, but these are all the buildings in Joplin. Here you can see this is every power pole in Joplin, so we're operating at the community level. Here are the substations. I believe there's 18 here. And then we can put it all back in. And again, the graphics, this is a workspace, so the graphics are fairly coarse, but detailed eventually. And then here's an idealized tornado model that was developed as part of the center. And then here is in blue, you see the Joplin Winfield map shown from investigation. And so we can do a damage analysis. We can look at using Monte Carlo simulation. On the top right, you can see this is the probability of exceeding a particular damage state, in this case from 1 to 5, or excuse me, 0 to 4. And then we can look at substation probabilities of failure. We can look at pole probability of failure. So we're calculating probabilities. And then we can look at their interdependency as well. We can do this for the Joplin tornado, as you see, overlaying the wind speed. And of course, this is pulling from fragilities and sampling and using interdependency based on location in this case. And then these damage models then propagate to the CGE economic model to look at things like percent reduction of household income or percent reduction of employment. And those have been validated. It was a hindcast. We know what happened to the economy. We can then propagate that into population dislocation. And what you'll notice is that in the population dislocation, it's not just people in the tornado path that dislocate, and that's a function of the economic model. They're losing jobs. They're because of businesses that are closed, because we actually do have data on basically where people live versus where they work. See, let me move forward there. I didn't mean to restart that. There we go. So, so now I want to, you know, as the expression goes, go down into the weeds for just a minute and show an example. So this is one example, and all the work that you see here is done using the NCORE platform as a research tool. So it's being used by, actually in this case, one of my graduate students to do this work. So we'll talk a little bit about building retrofit, the hazard, and the recovery. But drawing your attention to the bottom left plot, you know, as engineers, we work a lot, especially in earthquake engineering, we work a lot at the retrofit level, trying to increase the, you know, the robustness or harden the physical infrastructure. And then we're also pretty good at modeling this drop. We know what happens, but where the challenge is in community resilience modeling is modeling the recovery. And so I'm going to talk about the recovery today. So to give some quick background for those not familiar with tornadoes, especially around the world, you know, we have in the U.S. we have the highest percentage of tornadoes of anywhere in the world. So in 2011, there was a massive EF5 multiple vortex tornado. NIST did a big investigation of this and put out an excellent report that's available on their website. There were 161 fatalities, more than 1,100 people injured, and it was the costliest single tornado in US history. So the population of Joplin, it's interesting that it's 50,000 in the daytime, but then it balloons to 3 to 4 times that size in the daytime. It's 50,000 at night, excuse me. And that's simply, it tends to be an industrial or a work hub. And so it makes the CGE model all that more interesting. So we developed a suite of 19 tornado fragilities, because tornado fragilities, there were wind fragilities have been developed quite a bit, but there was very little for tornadoes. So this was started back in 2011. This is the more recent work, just a series of efforts that model that, and it's done with physics-based modeling, but it's equivalent static procedures that are done with an amplification factor from a tornado numerical, or excuse me, a tornado simulator at Iowa State University. And so here you can see this is what we call the scar from the tornado on the ground. Those are the damaged buildings. You can take a small area and zoom in, and here we see what we call strip malls, as well as some houses. And so we'll take a look at these. We can then pull up a particular house, and we can show that we know the exact details. And then based on those details, we can map fragilities to that. And so we do that for every building, all 40,000 buildings in Joplin. And then they're either color coded or just kept track of. So here you see on the left that this is the built environment. These are the 19 building archetypes assigned to the city of Joplin. And then on the right, we have our social science information about the households. And we have a lot more than this, but this is the basic idea is we know what's owner occupied, what's renter occupied, as well as the housing, how many, and then we know how many are vacant and details. And so we can go through and as I showed in that simulation example, or that graphic video, we can see that there's the building failure probability for, say, being in damage state 3 on the left. And then on the right, we can see the buildings that are associated with which of the 18 substations. And so we'll also model that dependency. So this gives you an idea of, this is the architecture of INCOR. So this shows what was just demonstrated, going all the way to the CGE model, the social science. So we start on the left with the built environment, and then this is the fragility modeling and the damage into the functionality, and then the economic and social science model. And so what I'll show in just a second here is we're going to go through and we're going to step through time to try and model the state of the community recovery, and then look at a series of different policy levers that can be implemented to try and change the trajectory of that recovery. So, so this is, I won't go through the flowchart obviously in detail, but this is the basic idea of what we're doing with this. And it goes through and we look at combination of delay time as well as repair. So the delay model, you heard a little bit from Greg for commercial buildings about the READY model. This is using something fairly similar. It is the READY model, but what we do is so the inspection, the engineering mobilization, and the contractor mobilization and the permitting are all functions of the level of damage and things like that. But the financing is actually a function of other things. And in this case, it's a function of the household income. And so what you see here is this table based on household 1 through 5, the different household incomes is a function of, well, it's gathered from data from the state of Missouri. And so it's fairly accurate. It's not perfect, but it's what we have at this point. So you also heard Seth talk a little bit about the census block level, that's as far down as we can go. And so we use that. We'll go in and take the housing unit IDs. We go through, we know the number of people, and we can then go through and assign, basically assign, excuse me. We can then take the households and de-aggregate them to the building level. And so here you see a census block, and we're doing this so that we can de-aggregate and get the building level. At the building level, we can get the household income, because that's what we're going to use for the analysis. So here we see, this is the damage description. We're using the functionality for the repair module. And here you can see the different repair fragilities. These were developed by Maria Collegiate when she was here for several years with the center. And this is the delay, or excuse me, the recovery time statistics for single sample buildings. And so here you can see they're fit to a Weibull distribution, but this is the mean damage level at the mean damage level for excuse me, sorry, something in my throat here. So this is this would be an area, a single building. And so this is the delay time, and then this is the delay plus the repair time. And so this would be something that was near the center of the tornado path. And then this would be something that was maybe more in, say, the, several hundred meters to outside of the path. So we can look at different policy levers. Here you see, so this just shows an index 1 through 5, and we have 6 different cases. So these are different policies, and then each case has a different policy combination that can be put in place, and we can do what if analysis and different scenarios. And so here we see, this is the community residential recovery for 4 of the different cases. I should maybe jump back. Yeah, it'll let me jump back to show you that case 2 is just retrofits. So that might be hurricane clips or things like that. Case 6, we're throwing everything, the whole kitchen sink at it, so to speak. And then case 3, case 5 is doing things like relaxing building permits, hiring extra building inspectors. And the way we do that is we take that data from READY for the mean value of time, and we either can cut it in half or reduce it. Like if we eliminate If we eliminate relaxed building permit, then we set that to 0. And then we keep the COV constant is the approach we use. And so here we can see the residential building recovery in years. We actually step through time by quarter here, which I'll show you here. So this is the time stepping going through 2 quarters and 3 quarters. And this is the probability of being in that state of recovery. And so for every building we're going through, and it is tracking the uncertainty the whole way through. And so what this does is it'll allow us to then take this, link this with other things that also have their distributions as we then model the rest of the recovery. And so this is just residential. We're in the process of using data-driven models to do this for business recovery as well. And so one unique thing about a hindcast, as I wrap up here, the one unique thing about a hindcast is that it allows us the ability to see if we were correct. And so we essentially, transport ourselves back, 10 years ago, 9 years ago, we take all the data prior to the event that's known, nothing, we don't use anything from after the tornado. In this case, there was every 6 months, there was video data recorded by a different group. And you can see that's the buildings in the red. They didn't go out to the edges of the tornado path, so we don't have that data. So we compared what you see in the red. And here you can see our analytical results, doing a blind analysis, as we call it, versus the empirical results. And of course, one of the things we can't model with the current approach is when people decide, due to reasons that we're not modeling, to not rebuild or to move out of the area, population out, migration, things like that. And that's where our social science team comes in. So to conclude, I just want to say that resilience analysis requires modeling from before, during, and after the event, such as a flood or a tornado that you saw here. Physical building and network damage to model this, no matter how comprehensive, and I think you heard this in a few other presentations, it's only a portion of the story because, as a few people have said earlier this morning and this afternoon, resilience, especially community resilience, is about the humans themselves. And then recovery modeling requires a combination of at least these 3 disciplines, but probably more, to account for community and household decisions. And you saw that gap, that 15% that decided either not to rebuild or something happened. And then resilience is best assessed when decision support is provided from models that operate at the intersection of these, not one group doing it, but that intersection. And so really the interdisciplinarity of community resilience. And so with that, I want to thank the organizers for allowing me to present some of our work. And again, this was just one example from a student, or maybe 2 students actually, and acknowledge NIST's funding, and also Lisa Long here at Colorado State for her contribution on the tornado example. Thank you.
Thank you, Professor Van der Lindt. What you're showing is very impressive. INCOR has come, I think, quite a long way, and it's really great to see what you're doing. There are some questions here. So the first one from Rajiv Garg, it says, thanks for wonderful work, Dr. John. Kindly provide some insight for using the economic risk model for the COVID pandemic. Has it been used by you?
Yeah, that's a great question. So it's not been used by me, but our economics team is actually doing COVID work with the CGE model. They're modeling, I believe, the part of the state of Colorado, as well as the city of Fort Collins, and they're doing some other regional and city work around the country. And it's actually, I don't know if I can go back without causing too much trouble, but it's interesting. If the setting up the model is the hard part, but once it's run, sorry, I didn't know it was this far back. Yeah, here we go. Yeah, so if you look at the model itself down on the bottom right here, the firms, these are the companies that are, and so if you take take the different sectors and you just shut them down in the model and then allow it to propagate forward, you're actually essentially modeling and of course, a few other changes, but that's the basic idea. You're modeling, the effects, the economic effects of COVID-19, and so you could, so that's they're doing it. It's a little more complex than that because you have to take into account changes in population and things like that because people do, move, they move, or they're vacating properties, things like that. But so it's more complicated, but that would be the simple version. So the short answer is I'm not, but our groups are not as part of the center. This is other work.
So the next question is from Mustafa Naim Abdel Moti. He says, thank you, Dr. John, for the elaborate insights. I have a question though. How do you adopt the same models to incorporate different hazards like flood hazard, for example?
Yeah, it's a great question. So that's one of the reasons we have different test beds is so we can explore the differences because with a tornado, a large portion, it's a wind event, so primarily a wind event. And so most of the households and businesses are covered by insurance. When we get to flood modeling, that's not the case. And so what we're using for recovery is we're using more empirically driven model, logistic regressions based on race, ethnicity, other things, but those also present their own challenges because the uncertainties between those types of models and some of these physics-based models are they're not done the same way, and so that's an area of active research for the center.
So there's a question from David Bonowitz. To model the 40,000 Joplin buildings based on the fragility types you created, do you do that by hand? That is one by one with human eyes, or do you use some sort of artificial intelligence system that looks at a street view and automatically classifies the building? So
Joplin was done individually. That was 4 postdocs in a conference room for about 10 days. And so they went through the 40,000 buildings. But for flood, for example, we use a mapping algorithm to determine, and so we, for example, we're able to do 500,000 buildings in Santa Clara County, and so it depends on the hazard, for instance, and then we also have data sets that we can purchase data sets. There's a company called Atom Data that we purchase data from, and that's primarily for the CGE data. But it also has enough building data. But again, often it's not perfectly up to date, so we don't know if there's been retrofits and things like that. And so there's some uncertainty there. We have explored AI, like Great Deerline was talking about. We've explored some AI as well, but we found for tornadoes that the tree coverage in a lot of these communities makes it very difficult to identify the roof type, and we only had about 80% accuracy, which from an uncertainty perspective, that exceeds the level that we were willing to take, at least.
Okay, and so the last question comes from, because we need to switch to another speaker, comes from Ahmed Abdelhadi, and he says, thank you for the nice presentation. I have a question related to the Joplin tornado damage hindcasting. Typically, these tornadoes are part of a large thunderstorm cell that involves heavy precipitation. So is the damage from rainfall considered in INCOR?
So right now, we don't consider that, but we have a plan to put that in. In the case of Joplin, we have some rainfall models, rainfall damage models that were developed for hurricane. And essentially, most of the rainfall damage will be out on the edges of the tornado in the EF1 and maybe 2. And then when we get to EF3, the roof's gone, so it's the rainfall's not as relevant, the rainfall or the water damage. So we feel like we should be able to apply that model, but we've not done that yet. So it's a nice question also.
Okay, thank you, John. Thank you very much. Great presentation, and I look forward to the panel discussion in just a little while.